Okay, so in this video, I plan to get a little more technical and in-depth instead of just solving the problem. So I just want to make some connections between determining whether lines are parallel, perpendicular, or neither, and conclusions we can make concerning systems of equations. Now, usually in algebra textbooks, these two topics are kept separate, but as you can tell, they're very similar, they're very related. So let's see what I mean. If I were given these two equations and I was asked to solve the system of equations, well, the first thing I'd do is, well, perhaps I'd apply the elimination method or the substitution method. That's one great way. Or I can check if one of these equations is a multiple of the other. So just by observation, it looks like if I were to multiply equation 2 or line 2 by a factor of 2, I would achieve equation 1. And you can also write that out like a proof. So if I were to look at line 1, is it the same as line 2? So negative 4x plus 10y. And I know this is simple, it's really clear to see, but just for emphasis, it's more of a conceptual thing. So if I were to divide each term by 2, let me just prove that I get L2. So this becomes negative 2x plus 5y equals to 9. Wow, so therefore line 1 is line 2. It's algebraically equivalent. In other words, it was the same equation as L2, but it was simply multiplied by a factor of 2. So when given a system, when a linear equation is a multiple of the other, this suggests they are algebraically equivalent. In other words, they are the same equation. Line 1 is line 2. So therefore, what else can we conclude? Well, first off, we can conclude their slopes are the same. They're the same line. So we know M1 equals M2. If we wanted to answer our original question, we know that M1 is equal to M2. They have the same slope. Therefore, L1 is parallel to L2. But more specifically, we could talk about what does this mean in terms of solutions? Well, if the slopes are equal and the lines are spaced apart from each other on the coordinate plane, then they never intersect one another. But in this case, since the lines are exactly the same, in addition to this, we know that the Y-intercepts are also equal. They are the same line, they are identical, so the lines actually overlap. The lines overlap. Therefore, or hence, they intersect at infinitely many points. Therefore, there are infinitely many solutions. Again, when you're asked how many solutions there are, that's usually a similar, very similar topic in a slightly different section or chapter of your book. So yeah, what happens if the slopes are equal? One more time. If the slopes are equal and the y-intercepts are equal, the lines are the same. If the lines are the same, they overlap. And if that's the case, there's infinitely many solutions. And that's the same as saying our system is consistent, meaning a solution exists. More specifically, there's not just a solution, not just one solution, there's infinitely many solutions. The lines overlap. They're equivalent. This is called dependent. When the lines overlap and they're actually algebraically equivalent. Now, one more thing. I know this is really abstract. What if so again, this was our scenario. It must have been the case that we were in the plane. We had two lines in the plane where they had equal slopes and equal y-intercepts. Your y-intercept is the point where you intersect the y-axis. So there's my line 1, and this must have been my line 2. They must coincide or overlap. If they have equal slopes and equal y-intercepts. Now, the other situation is, what if they have equal slopes? Actually, let me draw this better. What if they have equal slopes but different y-intercepts? Well, maybe this is my line 1. And perhaps this is my line 2. Hold on, I don't want to make it crooked looking. Let's do this proper. This is my line 2. Good. I can see where my line 1 intersects or intercepts the y-axis. So this is my y-intercept. Maybe it's something like, I don't know, +3 on the y-axis. But look at my line 2. Here's the y-intercept for line 2. It touches the y-axis at maybe, I don't know, like -1. So in this case, our system of equations could represent two lines where slope 1 equals slope 2, but they have different y-intercepts. So in that case, what can you conclude about the system of equations? Well, parallel lines will never intersect. So we can conclude that these lines will never cross, and therefore there's no solution. The system of equations has no solution. When M1 equals M2, but the y-intercepts are not equal. And this is called independent because in this case, the lines aren't the same. They don't overlap. They're different geometric objects. So this is called independent. They're different lines. And it's called inconsistent. Inconsistent means there's no solution. There's no point of intersection of the lines. And finally, one more scenario. I just want to tie everything together. This should be more of an introduction video. I should do like a lecture or a theory video. The final case would be if the lines are perpendicular. So perhaps this is the case. Maybe this is my L1. And that's my L2. So suppose these intersect at a perfect right angle at 90 degrees, then I would say, again, what were we concluding for these problems? We just had to say, oh, okay, if M1 times M2 equals -1, then we can conclude that L1 is perpendicular to L2. And that was it. That was our conclusion. But again, if we want to take it one step further, well, if they're perpendicular, that means they do share a point of intersection. We weren't concerned about anything except the fact that they intersect specifically at 90 degrees. But the fact that they intersect in the first place means there's geometrically a point of intersection. This means algebraically, this point is the solution to a system of equations. So in this case, we have one solution. They cross at one point. So in terms of systems of equations, this is our conclusion. We have one solution. If we have a solution, that means the system is consistent. And the lines are not the same object. They are different lines with different y-intercepts. So it's an independent system. So that's a crash course. I know it's really abstract, but all the possible scenarios. And of course, if your conclusion is neither, the lines are neither parallel nor perpendicular, then you wouldn't really be interested in these situations anyways. Well, yeah, if it's neither parallel nor perpendicular, maybe it's the case that they do intersect at a point, but so they do have one solution, but they don't intersect specifically at 90 degrees. So of course, there's many cases where the lines intersect at other angles, and so you would still have the same conclusion. One solution, which means consistent and dependent in this case.